Welcome, ladies and gentlemen. If you're intrigued by cryptography, you're in the right place. Our next talk is titled Encrypted Computation, What if Decryption Wasn't Needed? We're joined here today by Katharine Jarmul, Principal Data Scientist at Thoughtworks. Let's welcome her with a round warm of applause. And Katharine, the floor is yours.
Thank you, Johan. Awesome. So I hope you're ready for some cryptography. First, I would like to ask, is anybody in this room a cryptographer or has studied cryptography? Yes. 1.5, maybe more. Cool. So today we're going to talk about a field called encrypted computation. This is a field that I worked in for a long time. I'm going to try to give you an overview of the field, and it's going to be a little bit fast. So if we run out of time for questions, please come find me afterwards. I'm very excited to talk about this field. So what I want you to think about today and what I want to open the possibility of is, what if we could do data science and machine learning on encrypted data? What if we actually never, ever needed to decrypt the data in order to run the models that we're going to do, or in order to make inferences, or analytics, queries, any types of things that we'd like to do? And I'm here to tell you, not only is it possible, it is already running in production in many situations. So what is the field of encrypted computation? First and foremost, it opens up new possibilities for us. So here we're kind of exploring what would be possible if we could do all of this on encrypted data. First and foremost, my favorite use case, currently we have a ton of insecure data sharing. I make an agreement with your company, we decide to share data, we do all of that in plain text. What is preventing you from using that data to do something else? Contractual agreements. We have literally no technical measures usually in place when we form these data sharing agreements, other than there is some semblance of human trust. Cool thing about encrypted computation, we can model human trust in technological trust in cryptography. That is essentially the whole purpose of cryptography. Another thing that we can do is, a lot of times the sensitive data that we'd like to use, and if you've been working in data science for as long as I have, or even some number of years, you probably notice the more sensitive data has interesting information to solve difficult problems. When we think about healthcare, when we think about finance, when we think about the things, if you were at my keynote this morning, government, NGO, we're talking often about highly sensitive data. We're talking about using that for things like machine learning or statistical modeling. And for that, we need to try to hopefully provide some type of security and privacy for the people involved. Another thing we can do in encrypted computation is we can explicitly define the privacy and security rules and properties that we want to see in the processes and the computations that we run, and we can validate and verify those within our computation. This is not possible if we were just lazily doing plain text. This is only possible when we have strict definitions and rules around at what point in time we can do things like see the plain text, unveil the plain text, and therefore we can also model this in so-called logic that allows us to then prove that indeed the system is following the rules correctly. And finally, a concept near and dear to me, we want to empower users with their own privacy. So we want to give users the ability to share data with us without essentially us being able to see the data. And encrypted computation allows us to do all of these things. And in the center of it is, if you're here because you like math, maybe, in the center of it, there's some really cool math properties of cryptography, obviously. And we can call it magic, but as we know from machine learning, or as you probably know from all of your work in mathematics up to this point, it's actually not magic, it's just math. So the first thing I'm going to show you is an application that's already running. It's Hugging Face, which I'm assuming we have some familiarity with in this room. And it uses also an open source library from Concrete ML that is a product of Zama. And Zama AI is a group of cryptographers that are based in Paris who are working on some pretty cool machine learning problems. So we're going to go to the Hugging Space, so you can run this on your own. This is a Hugging Face space. And this Hugging Face space allows you to do some basic sentiment analysis with encrypted tensors. So the first thing that we need to do is generate keys. We can then provide a message. So I really like encryption, I think. And we'll try to give it something a little bit more tricky. We're going to encode, quantize, and encrypt the initial embedding. And then we're going to run the FHE evaluation. More on this later, but the FHE stands for fully homomorphic encryption. It eventually runs, and we have our encrypted predictions. So as you can see, here's an encrypted vector. And then at the end, we can decrypt it on our side, and we see that 72% positive, and so on and so forth. And so this is already running. You can actually test this out yourself. But you might be wondering to yourself, how does this actually work? Well, I want to start to give you a mental model to work through that could maybe help you understand homomorphic encryption, and then we'll move to other forms of encrypted computation. The most important thing, obviously, is the homomorphisms of the properties themselves. And this is best shown in commutativity, which is harder for me to say now that I know German, because somehow my brain wants to turn it into commutativity, and that's not right. And so we have our inputs, which here in plain text space are our X and our output Y. And we have our ciphertext across the bottom, C1 and C2. And the commutativity property allows us to move between ciphertext space and plain text space and perform functions that end up creating the same properties. Now, those functions may need to be shifted slightly when we're working in encrypted space, but the concept of homomorphism allows us to end up performing the same amount of operations in encrypted space as in plain text space, and to make sure that we end up with the same result. So the cool thing about when we think about encrypted computation in comparison with some of the other privacy technologies like differential privacy is we are not reducing our accuracy in order to get the solution. However, it is more expensive. More on that in a second. So how does it actually work? What I thought is we'd walk through an example of palier. So palier encryption is one example of homomorphic encryption or crypto system, encryption scheme. And here is the basic equation that we use for palier to encode or encrypt data. So first, we have our encryption message. That's the M, and that's in plain text. Of course, we've also created it in some sort of binary space or some sort of byte representation, and that's what we take as our message. We have G, which is our finite group base. So I don't know how many people here have studied much of group theory or finite fields or number theory, but yes, but this is your group, right? And that's an important method in thinking through cryptography, because quite a lot of the cool crypto math is based around groups and things like modulo arithmetic and so on and so forth. Then we have our randomness R, and we're not going to get into how that's sampled, but there's particular ways that we need to sample that. And then we mod our n squared. And our n is our modulus. It's generally a large prime. And if you know group theory, it divides the order of G. So in this case, because palier allows us only to do one type of homomorphic encryption or one type of homomorphic property, which means it's partially homomorphic encryption, we're going to kind of cheat and take a shortcut. We're going to choose a large prime, n, and then we're going to add 1, and we're going to get G. And that's how we can define our group base and our prime. And the cool thing is we can immediately see we're going to take an encrypted message 1, we're going to take an encrypted message 2, we're going to multiply them together, and through some fairly simple algebra, we're going to define or figure out that when we take encrypted message 1, so ciphertext 1, and we multiply it by ciphertext 2, we actually end up with the ciphertext of M1 plus M2. So the addition of our two original messages we get by multiplying the ciphertext together. And this will always work, which is pretty cool. But you don't have to just trust me. We can try it out. So I wrote a book called Practical Data Privacy. In it, there's an entire chapter on encrypted computation. It goes much more into details than we'll have a chance to do today. But as part of building that chapter, I've also built a series of Jupyter notebooks that are available online that you can use to play around with these concepts. And so this notebook has a little bit more above it of defining a variety of functions and showing you a little bit of how fields work. But today we'll just start with generating the keys. Sampling randomness. Oh, can you see this? Is it big enough? Hold on. Maybe that's better? You tell me in the back row, can you see it? Okay. So we have our encryption keys. So we can see I have n defined, I have n squared defined, and I have g defined. I can sample my randomness via a particular method. I can take a message of 4. I can encrypt the message of 4. I can see that the 4 is encrypted. I can decrypt the message, and I get the result. Now you're like, Catherine, okay. I can encrypt on my own. I don't need your Jupyter notebook to encrypt things. Okay, yes, this is very, very true. However, maybe you're intrigued or interested in the actual homomorphic properties. So all of this is written with a cryptographer that I know, so it is definitely correct-ish. And you can use it to play around. And maybe you're curious about some of the mathematical operations. So all of it's been written in as easy as I can write Python for you to go through. But we take our first message, we take our second message, we sample randomness for our 2 different ciphertexts. We encode these, or encrypt these, essentially, into ciphertexts. We have our 2 ciphertexts. We add them together. We get the result also in ciphertext, and we decrypt them, and we indeed see that it is equal to the same plaintext operation. We can also subtract them, and we indeed get the same operation. We can also, one cool thing about Palier and several other of the homomorphic encryption schemes that are even only partially homomorphic, is we can also do as many plain text operations as we want. So we can take encrypted text, we can multiply plain text, we can add plain text, we can divide plain text, we can subtract plain text, and we end up getting the same result. So we can go through times 5 minus 1,000 plus a very large number. Well, a partially large number. So, it's very cool, no? No. Yes? No. Okay. Maybe partially cool. So we'll keep going. We'll learn a bit more. So I want to give you a brief recap. So homomorphic encryption, what is it? It allows you essentially to perform these types of mathematical operations on ciphertext without having to decrypt it. At any point in time, the decryption key is yourself, or you have it yourself. So we can think of it in like a user and an owner and an operator situation. We could have a situation where only one of these people has the decryption key, and therefore only one of these people is allowed to decrypt the result. And there's some pretty cool things. So these are all properties of a particular crypto scheme. Not all crypto schemes are homomorphic, obviously. And some crypto schemes provide what we call fully homomorphic evaluation or encryption, and others that only do partial. So Palier, which I showed you today, we don't actually recommend using it anymore because it's based on factorization as the hard problem, which of course will eventually one day be non-quantum safe, but it's still a fun place to get started and to see. But Palier will only ever support these additive and subtractive properties. Therefore, when you get into more complex crypto schemes that allow you to do multiplicative operations, or what we call evaluations on circuits of arbitrary depth, which basically just means arbitrary complexity, length, and difficulty of the operation, these are when you get into the really interesting problems, and this is what Zama AI, for example, is working on. Some of the problems in homomorphic encryption that we've encountered in the field, so to speak, is that for these operations to perform at any relative amount of speed, you might require hardware accelerations. So for example, Zama, as well as several other, Microsoft has a group that also works on homomorphic encryption. They are often working with FPGA developers and other types of people that are creating specialized hardware for specialized use cases to run this at scale. There's also some homomorphic encryption protocols or operations that are just easier. So if you can define the problem with non-arbitrary depth, but with a particular amount of what we call circuit depth, then you can also speed it up by just designing the problem slightly differently. And again, just to repeat, homomorphic encryption is really awesome when you have you're a processor, you want to offer your user or the data owner or whoever it is a way to use your processing without having to decrypt their data, homomorphic encryption is actually a great fit for those types of problems. Okay, secure multi-party computation. So, homomorphic encryption is a part of encrypted computation. How many people in this room had already heard of homomorphic encryption at least once? Yes. Okay, a smattering, if you will. How many people have heard of MPC, or secure multi-party computation? Hey, more than normal, yes! Okay, so MPC is actually the space of cryptography that I had the pleasure of working in. It has a lot of cool properties that are very different than homomorphic encryption, in that, by default, MPC schemes involve multiple players. There is no way of building a multi-party computation without having multiple parties. And the cool thing is that it has some significant performance improvements in compared to homomorphic encryption. So instead of essentially having to perform all of our operations on these very, very large, sometimes ciphertexts, we're actually providing them or performing them on things that we can size more reasonably, often called things like secret shares or other types of operations where we might trade between MPC and homomorphic encryption. Another cool thing is because it automatically has multiple parties, it's great for data sharing use cases. So in the area that I worked in encrypted machine learning, we were often dealing with situations where we had multiple data providers that would like to train a model together, but there wasn't full trust between all of the data providers. Maybe they were competitors, maybe they were, you can imagine, fields where they were vertically integrated, like supply chains and so forth, and they might want to share data to solve a problem, but they definitely don't want to share their data in plain text because it could involve some sort of competitive problem between the different data contributors. And so this makes it really, really great for things like data sharing cases or other things where multiple people that might have a variety of levels of trust of one another can decide to compute together and all benefit, or at least decide who gets to benefit from the result. It's based on the same mathematics, so a lot of the same ground principles of number theory as well as abstract algebra apply for MPC. But the cool thing is like we move away from this kind of old, well, it's not old mindset, but this mindset where we need to have a public and a private key. In MPC, there's a different way that we kind of model these problems, but we still have the ability to decide when and how we decrypt and who is allowed to decrypt. Okay, so you might be thinking, okay, all of this sounds cool from a theoretical perspective, but how can we actually imagine what we can use this for? Well, the field that near and dear to my heart is encrypted machine learning, and I want to kind of break it down into two boxes for you. One of them is where we actually want to train an encrypted model on encrypted data, and that is this big bucket of encrypted training. And one which we call usually encrypted or private inference. And this is where we just want to use maybe a model that's been trained on plain text, maybe that's been slightly altered so that it can handle whatever ciphertext we're giving it, but primarily a plain text model that we then want to show an encrypted tensor or embedding or something like this and actually run a prediction on it that only one or multiple people can decrypt based on how we've formed the problem. And that's very much like what the Hugging Face Zama interface does, is very strongly in the encrypted inference, where they've made some very slight changes to the way that the initial input layers work on the Hugging Face models, and everything else remains the same, other than now it can run on encrypted tensors. For encrypted training, what's really cool, I mainly worked in MPC again. This is where I would strongly say distributed or decentralized use cases where you have multiple people that would like to contribute data as part of your model training. This is where it really works. And because in MPC we have the trade-off, we have less compute overhead, but we have more interaction, which basically means more network, more latency problems. When we move people to the same cloud, let's say you have multiple people on Azure together or something like this, we can actually significantly reduce the latency overhead, and therefore we can actually quite often speed up MPC use cases to near production times that you would normally do, especially if you're doing batch training or something like this, and you don't need to do any type of real-time training, which almost nobody is doing anyways. For homomorphic encryption, it again is, you're going to have to start to make some trade-offs, and this is mainly because homomorphic encryption, you're going to need to think about hardware accelerators, you're going to think about specialized hardware, and you're going to potentially move into an area of homomorphic encryption that's been growing with certain protocols where you essentially want to make trade-offs and say, we're going to lose some accuracy because we're going to allow for an increase of noise in our ciphertext, because one of the most expensive operations in homomorphic encryption is the reduction of the noise that happens over time after many, many, many operations on the ciphertext. One of the areas that I had a chance to work in as well is thinking through, we have a distributed or a federated machine learning problem, and we would like to create some sort of updates or aggregates across all of our users or across a few disparate groups who would like to train a model together. One of the cool things is that you can look up, and that's also, of course, in the book, is secure aggregation. So the idea of secure aggregation in federated learning is the ability for us to send our updates, whether it's a vectorized form of the weights that are encrypted or whether it's a particular gradient update that's encrypted. We can send the updates to the aggregator. The aggregator is in charge of working on those updates, deciding, okay, we're going to move in this direction, we're going to send this update to everybody and update the global or the shared model, and then send it back out again. And what we can actually do is we can formulate this problem so that all of the updates that are sent are encrypted, that the aggregator has a protocol or an ability to decrypt that only after, let's say, the federated average is computed, and then everybody can get the update and continue learning together. So this is a pretty cool thing, and I worked with the team that created the first secure aggregation for TF federated, if you want to talk about it. Another cool thing that you can do that you might not know that you can do and is actively a part of the Google Ad, let's say product, we can name Google Ads a product, is private set intersection, otherwise known as private joins. What we can do with private set intersection is we can take a group of identifiers that one company has with a group of identifiers that another company has. Of course, these have to overlap in plain text space as well. We can encrypt them, and we can share them using a variety of protocols, and we can actually end up finding the intersection in ciphertext. So we don't have to actually reveal the plain text in order to find the intersection. And for example, in Google Ads, what they might be curious about, I don't know, but maybe what they might be curious about is users that clicked an ad along with users that bought something, and they're trying to find this intersection. Why are they trying to find the intersection? Well, at some point in time, they'd like to potentially think through ROI, or the value of a particular ad, or the influence of a particular ad. So particularly when we're dealing with offline sales and online ads, what is the influence of online ads and offline sales? This is a hard problem, right? And so one of the ways that they've been able to do this is finding these joins with the private set intersection. And one of the things you can do then is you can then decrypt, and then both sides know the people that bought something and the people that clicked. But what you can also actually do is you stay in encrypted space and you keep computing. And you just take that encrypted, essentially, union that you have, and you have encrypted and encoded the other information, such as the sales data or the click data. And then at that point in time in encrypted space, you can do things like calculate the average. You can do so even with differential privacy if you'd like to add some anonymity to the process. And then you can decide who gets to decrypt and who gets to see the final ROI. And all of this is possible and running in the Google Ads ecosystem today for particular use cases. But moving beyond, we can do other things. We can do things like encrypted auctions. This is something that the Zaman colleagues recently worked on, where for a variety of cryptocurrencies, they wanted to create encrypted auctions where people can create encrypted bids, where the top bid can be evaluated in comparison with the other encrypted bids. We can even validate that indeed the bid that you sent is yours and that you were the one that encrypted it. There's a few methods to do that. And then finally, we can decrypt and reveal the top bid. This is also how the Danish beet auction ran now more than 10 years ago, is encrypted auctions in an MPC setup. There's numerous other use cases. You might be familiar with the problem. You have people, or you're at your work, you have on-prem data, you want to move it to the cloud. You are not allowed to move it to the cloud for a variety of reasons. Privacy maybe being one, security policy or proprietary data policy being another. Another thing that we can do is we can think about what functions can we encrypt and then move to the cloud for elastic processing and then move back to on-prem and decrypt. We can also do this in any type of distributed operation. So particularly when we think of MPC, and maybe inspired by my keynote this morning, if you have critical problems that you're trying to solve, like energy grid problems, housing problems, education problems, you would like people to contribute data that is extremely sensitive to them. How are you going to actually get people to want to contribute this data? Think about forming the problem in a way where they never have to share data without A, knowing exactly what the security protocols are, and B, never sharing data without it being encrypted. A few things, so I'm starting to run out of time, but I wanted to give you a few things that you're going to learn. I hope maybe a few of you are inspired, maybe you're intrigued. I want to tell you some things that you're going to learn if you decide to go on this journey from data science into cryptography. First, you're going to become an expert at noticing optimization and performance problems and trying to shape your problem into ways that will actually work in cryptography, which is pretty cool. You're also going to start thinking about combining approaches, and this may mean sitting with cryptographers if you get a chance to work with them, but this may also be sitting with libraries in cryptography that are available and start thinking through, okay, is this a HE problem? Is this an MPC problem? Is this a circuit problem? How can we combine these approaches and make sure that we have the most optimal solution? You're going to learn all about finite fields, so you're going to be moving from floating point arithmetic to fixed point arithmetic. For most of our stuff, especially like the buffer sizes that we have now for most of our compute, you're going to be fine. But the one thing you're going to think about is if you're dealing with problems that get really, really small numbers or really, really big numbers, you're going to get errors. And so you're going to have to start thinking about how you shape your problems so that they're scaled to fit the encrypted space. You're going to learn about security models. Like, how do I think through, does this need to be passive security? Does this need to be active security? What is the relationship between the different people that are contributing data? How can I think through threat modeling and also security paradigms to actually properly form this problem? And the most fun thing is you're going to learn how to debug on data that you have no idea what it is and that you cannot see, which is as fun and as difficult as it sounds. You can check out my book if you'd like to. I hope maybe you're inspired to look at privacy-enhancing technologies and learn more about encrypted computation. I've heard that there's some reading groups that have formed around my book at a variety of different workplaces, so maybe it's a good way. I've heard good feedback that it helps to learn with others, especially when you're sitting and going through some of this code, to have somebody else to talk with. So if you want to form a reading group, I would encourage you to do so, and I've been invited and go talk to some reading groups that have formed at a variety of companies. And then finally, check out Zama's Concrete, as well as there's a few other open source libraries that I would recommend. And again, every chapter in the book has at least one Jupyter notebook, if not many. And so I hope you'll find some inspiration there. I hope that that was exciting for you, that maybe you learned something. You can always reach out at any time, and I hope I have time for like maybe at least one question. Thank you very much.